Okay, so here, welcome. So today, as usual, I will recapitulate main concepts from last time, and then go to the new stuff that is a bit more details about how the training works with multi-layer perceptrons, so the full connect neural networks. Specifically, I will go into optimization algorithms that are not exactly a gradient descent. And then I will talk a little bit about regularization. That is always an important aspect in machine learning. And then probably I will start introducing the convolutional neural network. That is our first kind of dedicated architecture beyond the omniscient multi-layer perceptron. Okay, so first go back to the previous slides or previous. So we looked into how the training of a multi-layer perceptron works. So this is the sketch of a multi-layer perceptron. We have the input x can have any number of dimensions, and for the sake of the notation afterwards we call the input as the output of the zeroth layer. So this would be the zeroth layer that has an output that is the actual input, and then we have an affine transformation of the input, giving these z's by means of these weights wij, and then we have the activation process, so the outcome of the linear combination or affine transformation of all the input, including a possible bias, goes into the output. And this process is repeated. So the notation, I will try to always use z for the outcome of the affine transformation and y is the outcome of the nonlinear activation. So for our training, we have first a forward pass. That means that at some point we have weights that at the very beginning could be just all zeros or some random assignment. And then we go through layers following the structure above, right? So we go over layers from 1 to n, and then for each layers we go over all the nodes and what each nodes, so the j is the index of the node, k is the index of the layer. For each node in the layer, we first do this affine transformation by means of the weights, and then we calculate the activated kind of transformation of these z's, and this is done over all the layers, and at the last layer we have an output that is the these y's of the last layer. And then we evaluate the loss function, that is a function of this output and the ground truth, so the g. And now we want to know how to modify the weights. So our network is fully specified by the weights, and this is our parameters that we want to train. And so for doing that, we so probably I have it somewhere here. Yes. So our kind of master equation for the training is that we update the weights on the basis of the previous weights, and then we use the gradients of the weights, the gradient of the loss function with respect to the weights. And in order to evaluate this gradient with respect to the weight, we will use the chain rule of differentiation and the gradient with respect to the y's of each layer and the z's of each layer. So in practice we have the so-called back propagation, and at each layer, so here is the last layer to start with, we evaluate the derivative of the so-called divergence with respect to each one of the z's. So it is worth underlining that this divergence is the basically the per data point loss function. So keep in mind that everything that happens in this backpropagation is a reaction to just a single data point. So there will be a discrepancy between what that data point should give as an output and the output of the network. And this will give us how much I should change the weights in order to make the network give an output that is closer to the actual output for that particular data point, right? So this is where I jump between the small delta and the capital L. So the small delta is always per data point. Okay, so this derivative with respect to the z's, we insert the derivative with respect to the y's using Leibniz notation, and then we just recognize that this part is what we know because it will be our discrepancy with respect to the ground function as a function of the change of the outputs, right? So so this would be if we use a mean square error kind of loss function. That is the typical one for regression. We have the difference between the input and the ground truth. So the output and the ground truth. And then we recognize this derivative as just the derivative of the activation function alpha in that particular point z. And probably I didn't mention last time. So also this derivative will be stored during the forward pass, right? So the moment we go through, we will record all the zj's and all the yj's at all layers, as well as all the alpha prime, because that we know. So we know the shape of the function analytically and its derivative, and then we just store this data. So we have these values available, alpha prime. And then we have this derivative with respect to the z's, and we calculate the derivative with respect to the weights by, again, inserting the derivative with respect to the z's. One has to be careful with the indexes here to keep consistent, but yeah, it's just usual linear algebra. And then we just notice that the z's depend on the yij by means of the affine transformation. So we have a sum of these products, and then only if we take the derivative with respect to the yj, only one of the yi's survives. Right? And it is worth noticing that this would be from the previous layer. So when we take the derivative with respect to the weights, we maybe here. So the weights are the connections. So the weights will have maybe here is more clear. The same index. So the weights of the layer n, they project onto the z's in the layer n, but they use the input from the layer n minus 1. So this is why here you have n minus 1. And then to close the circle, we calculate derivative of the divergence with respect to the output of the previous layers. Again, we insert the zj's. We again notice that the zj's are this linear transformation, and the derivative with respect to the y's are the weights. So these terms here becomes the weights, and then again we know this derivative from the previous step. So putting all together, what we do is we start from the last layer, we evaluate the derivative of the divergence, so how much for the particular data point the output of the network is different from the ground truth. This will give us the derivative with respect to the yn. Then the derivative with respect to the z is that same thing we have just calculated multiplied by the derivative of the activation function, and the derivative of the weights, I forgot an n I think here, will be the previous step multiplied by the outputs of the previous layer. So we have all the values, right, and stored properly, and then we go back. So from the n-1 layers up down to the last one. So the first one, and we go over all the nodes in the layer. We calculate first the derivative with respect to the y's, we know them, with respect to the z's, and once we know that, we go over all the over all the weights. So when we have done this, I keep forgetting the layer index. This is a k. Yes. We put all together, all the derivative with respect to the weights will be our derivative of the overall loss function with respect to the weights, and then we can do the update. So in principle, this would be our backpropagation. So this is our backpropagation algorithm with a gradient descent. And then also from last time, many people have been looking into how much this algorithm, so more the steepest descent part, right? So how you do it in the network that comes out of the architecture of the network. There are no other ways to do it. But this is, of course, a choice. We could have done many other different ways. We could have done a Monte Carlo sampling. Turns out not to be the smartest in this case. So we do this kind of gradient descent update, and people have been designing situations in which this algorithm doesn't find the global solution. And so I chose maybe the most representative situation in which you have, so you want to classify these points, x and circles, and yeah, you would have a linear classifier with a dividing line, for example, here. And this could be found by both kind of global minimum algorithm, that is the one behind the perceptron. I didn't go into the detail, but they say that finds always this kind of solution. If there is a linear separator, it will always find it. The gradient descent will also find it, but now if you introduce an extra point that is very far away, say in this direction, the perceptron algorithm will find the solution. The gradient descent essentially will not find, because basically the change in error by moving a little bit this solution here to accommodate the last point is very small, and some point above, I mentioned that you stop the algorithm when the change in your loss function is smaller than a certain preset epsilon. And typically, okay, you can design the situation such that you are below this epsilon, so you will not update your loss function. I mean, take this as just like a meme or a way to remember that there are problems. Of course, you can say, yeah, I can do better and find it, but one can always find the situations in which your gradient descent will not find the actual solution. So the take-home message more like that the perceptron kind of algorithm will always find a global solution if there is a linear separation, very important. So it has low bias, meaning that it will find the right solution. It has high variance, meaning that wherever you put your data points, the algorithm has to react and find a new solution if it exists. While the gradient descent neural network kind of algorithm has low variance, so it will react much milder to change in the data. Bias with question mark, because it may not find the global solution, and in some cases it could be tragic. I mean, one can construct examples in which the solution is badly wrong given the training data. I mean, this is nothing to do with the fact that your training data may not represent the actual distribution, so your test data will introduce new information that your network or any machine learning model will not be able to simulate. Here we are just in the training, so your algorithm may not find a good solution at all. So then there is, of course, a big family of these things, of these situations. Solution, typically one does not care because there is nothing much one can do. Besides the algorithms that I will tell now that not really cure this problem, one can say, okay, start from a different random initial solution, from any kind of optimization that we do for atoms, for example, just not believe the first solution, just try again with some other random initial condition, right? So there is nothing better than that. Okay, and then another caveat or important point is that this gradient descent is basically designed to work when you have a convex function. So we kind of assume that you have, at least locally, given the initial conditions, a kind of convex function to optimize. And in the extreme situation, just to simplify life, where one has a quadratic function, of course you can always approximate with a parabola locally, you even have the optimal learning rate, right? So yeah, I should have repeated probably, but this is this term here. So the learning rate that gives, let us find the solution in this smallest number of steps as 1 over the second derivative. So in, well, 2 times the second, the second derivative, yes. So in a quadratic function, that would be just 1 over a. More important than that is that we have for not only a quadratic function, but in general a convex, locally convex function, that if we have a learning rate that is smaller than this optimal one, we will converge. So we will just find a minimum without oscillations. If you are between the optimal and double the optimal, you will find a solution, but you will oscillate on the 2 sides for each dimension of the function. But if we are above the optimal, we diverge, right? Because your prediction would basically let you jump further to the minimum, and this will cause the algorithm to explode, to diverge. Then you say, yes, of course, then I should always evaluate this optimal rate. You can always define it. So in many dimensions, it will be related to the eigenvalues of the Hessian, so the matrix of the second derivatives, or the trace, actually, to be clear. The problem is that you don't want to calculate second derivatives for a function with tens of thousands or millions of parameters, because this is the size of the Yij parameters that we want to calculate. A small neural network with maybe a few thousands parameters. You can really design one with maybe a few hundreds, but that's very, very specific. So thousands to millions or billions with modern transformers. And then you don't want to evaluate a Hessian that will go as the square of this. So you have to evaluate the square of this, then calculate the trace of that. So that doesn't work. So you may want to estimate this optimal learning rate in other ways. Of course, the literature of convex optimization is rich in this kind of remedies, how to kind of approximate the Hessian. And incidentally, people doing optimization of atomic configuration, they know, say, the BFGS algorithm or the low memory kind of implementation of BFGS algorithm that has kind of numerical estimate of the second derivative locally. You can find in literature that people have been using the LFBFGS algorithm for neural networks, but this doesn't look like to be very common. So it's still too heavy with the number of parameters that you have on a network in general. So what I will present rather is so-called, I had to make a selection, so interesting kind of, so again, probably I write this one again to keep in mind what we are talking about. So we look at say one improvement on this part here and one improvement on this part here, meaning instead of the actual gradient we use something else that depends on the gradient. We don't want to do extra calculations. And instead of in the way it is written here, it is just a constant learning rate over the whole optimization process. We will introduce some kind of adaptive learning rates or something that will change during the optimization. Just to give a flavor of the different algorithms, but actually I will get to the so-called adaptive momentum optimization. That is, so the acronym is ADAM. This is the one that you find everywhere in libraries. So just that you know what is behind ADAM, and I mean there are variants, of course, of ADAM, but like the basic I will present today. Right. So let's look into the maybe the gradient. WL gives us trend. Nope, wrong place. Algorithms. We should ban the letter H from the alphabet. It's completely useless. So the idea is to kind of update or improve this. Oh, there's a minus here. So let's say I will manipulate this delta V, W, right? I mean, I didn't write anything new for the moment. I'm just saying that there is an update here in the weights, and instead of being just eta gradient, we use something else that is some linear combination. Oh, maybe I put an index here as well. So this update will change in time, so it will be the update at the previous step plus probably put here and here there is a coefficient, say beta. So I use a fraction, so this thing is between 0 and 1. Typical value, just to fix the ideas, would be say 0.9. So I will use a little bit, so a certain fraction, possibly large, of the previous update, and then I will correct it with the new information. Now I think there should be a 1 minus beta that I have not here. Yeah, probably there should be a 1 minus beta. So the idea here is the following. So let's say that we have kind of sketch of asymmetric kind of so a function in 2 dimensions. So these are the contour levels. And so we want to get to the minimum here, and we are so the point is that we have the gradient in this direction is much shallower than the gradient in this direction. So if we have so if we are minimizing this function, let's say, and we have a kind of yeah, maybe use another color, some kind of update rule that follows the gradients in the two directions. We may have that in one direction we always keep the sign, and in some, so basically the sum of all the previous gradients will add up, and if we are in the direction that is much steeper, the sign will continuously change as the gradients, so this the sum of the gradients from the previous updates will cancel. So if you translate this into this equation, so you can of course unfold this one, this will be the sum of all the previous gradients with the smaller and smaller betas. So basically we are promoting situations in which the gradient is always the same sign, so they will this delta W will add up, and whenever you change continuously sign, this delta W will well, it's this term actually that will cancel with itself, and so you will build up momentum. So this is the so-called I should have probably this as a name. So within the class of trend algorithm, this is the momentum. Momentum estimate, or well, algorithm is also good. So you build up momentum in the direction, in the shallow direction, and dampen momentum in the steep direction. So the update will kind of speed up in the slow direction and slow down in the fast direction, so that you balance the achievement of the minimum. A related idea would be updating or adaptive eta. So this would the example, or yeah, prototype example would be the so-called RMS optimization or RMS propagation. So RMS is root mean square, the usual meaning in statistics. So the idea is to kind of reinforce this idea of the different directions, more shallow, more steep, also in the eta. So here we use so we define the expectation value of the gradient squared. So this would be a scalar. So the gradient modulus square would be the square displacement, the square cumulative gradient, and then we evaluate the average, so the mean value, and we use this in order to correct eta in this way. So we define this thing as a combination of the expected values at the previous step. So this would be the eta t plus 1, the one at t plus 1 minus the current gradient square. right? So again, we make a linear combination between the previous, so also this gamma is between 0 and 1, and again a typical value will be somewhat largish. So we try to be conservative essentially, and not react too much to the new information. So this would be the gradient, I don't know, I put it here at that time t, at that time step t in the optimization. And then the update actually would be that the W is W minus eta gradient L, so the usual stuff, but eta, so eta like a parameter that we give at the beginning, will be corrected by this expectation values at t plus some small value, because yeah, if this is very small, we don't want to have divergences. So the parameters would be, we give eta at the beginning, and then we update each step, so we dampen effectively. So this number is bigger than 1. This denominator is bigger than 1, and so we reduce eta at each time step essentially during the optimization. So this is the so-called root mean square propagation algorithm for the learning rate, and essentially combining these two would be the Adam adaptive momentum optimization or algorithm, and this works like this. So we have, just to write it down all together, a mu m use t is a combination of mt minus 1 with a beta plus 1 minus beta yes, and then we have the part on the mean square. So gamma, we use always the same notation, t minus 1 plus 1 minus gamma this is the w square. Yes, and then we have that the overall update of the weights is previous minus eta over v plus epsilon multiplied by mt. So v comes from this update, and m comes, so this m comes from this update. So all this, keep in mind, we use this the gradient with respect to w, so what we calculate with the back propagation. Here we use that same thing squared, so we don't do extra calculation except evaluating the square, the modulus square of this vector, and then we combine it in order to make the algorithm. So the general idea is to kind of promote directions where the gradient is shallow, and dampen those where the gradient is large, so that we arrive at the minimum without overshooting. Right, so then of course we have, so let me restate here, we have the beta gamma parameters and the initial eta. Okay, epsilon is not really a huge variable to parameter to change, but certainly beta, gamma, and eta one wants to play around. So typically beta and gamma are close to 1, and eta is small. Some typical starting value would be, say, maybe 0.1 or 0.001, something like that. It is already relatively small in general, and then it is further reduced, right? Because every iteration it will be reduced by this term here. Okay, so this is how already at this point an actual learning of a multilayer perception would work. So with this EDAM algorithm, with one extra kind of technology. So we now go beyond batch gradient descent. Is it the E or I? Descent or descent? Descent, I? DI? Like this? Okay, yeah, descent, yeah, thanks. So I haven't already introduced the point of batch, but the idea is that so we evaluate this, go back here, we evaluate the derivative of the weights with respect to a single data point, and then we typically go through over all the data points in order to get the overall gradient. So at least the basic or ideal gradient descent would have the change of the loss function with respect to all. So the loss function is defined by all the training data points, and we calculate the gradient to the weights as a reaction to this function of all the training points. So this would be called batch gradient descent, in which we go over all the algorithms. And then people notice, okay, I have to evaluate all those gradients because I give one data point, do the forward propagation, evaluate the gradient with respect to that particular data point, and then I do for another data point, I have the new piece of the gradients combined all together. I do a huge amount of calculations, and then I have just updated my W by a tiny bit, right? So let's try to speed up, or at least use more information and try to kind of use the training data better. And one can show that if you do the update for each data point, you will, how to say, you can speed up the gradient descent, because you will update the weights for each next data point. The weights are already updated, right? So you have already used the information from the previous data point. And then you go over all the data points, and you can see that for a well-behaved convex function, if you do that, so over one cycle, that by the way is called epoch in the machine learning lingo, you typically are a bit better, closer to the minimum than if you do one update, because some things cancel out, and so I mean one can go into the theory of that, but let's stay a little bit descriptive here. So now if you start a new epoch, you don't want to redo the cycle exactly in the same order, because you will induce some kind of periodic behavior, right? There is some data points that are a little bit the oddballs, and they will introduce the same kind of correction every time. So there will be some kind of periodic behavior related to the somewhat outliers. So you typically want to shuffle the order of all the data points. So you randomly shuffle, so you just invoke some kind of random number generator and do the reordering of your data points. So now if we do this incremental update, that means we update our weights for each data point. Plus whatever, random shuffling. We have the celebrated stochastic gradient descent. SGD also is an abbreviation that you see everywhere in the literature. So there is nothing mysterious behind that. It's just that the weights are updated at each for each training point, but we do this random shuffling, so that we don't have this periodic behavior. Now, if one looks, let's say, carefully into this stochastic gradient descent, so the one in which you change the weights for each data point, you can incur also in still quite some sensitivity to the training data, to some specific training data that you may want to avoid. So there is, as usual, an intermediate solution that is called mini batch. So this is a keyword that you see a lot in libraries and literature. So the mini batch as whatever subsets of training data. So nothing that really, I mean, of course, somebody has a publication that has a lot of citations, but at the end is, I mean, there is a strong statistical analysis that shows that it's always better than the full batch or let's say it's most of the time better than the full batch and incremental update. I mean, you always have corner cases, but so at the end of the day, you just say, I divide my data in whatever 10 subsets, and I do my update every for each of these mini batch. Okay, so this is so, and then of course you have to say a parameter here that is how many mini batch you have out of your training data, right? So this is just a little bit of going into the lingo. That is, I mean, at this level there is not much more to say. Of course, one can show that in most of the cases this mini batch approach is the best possible. So typically this is the one that you would like to choose, unless you have good reasons not to. Okay, last point about the optimization would be some discussion of regularization. So in general, the idea of regularization comes from, say, traditional machine learning, so not related to neural network, in which in general you have a loss function that is related to the some kind of so your model function, that is a function of some weights one way or another. This is what you fit or train, minus the ground truth, so some kind of error related to this ground truth. So it could be the 2 norm. and then in many situations we have more weights than training data, so we add so-called regularization, so some kind of constraint on the weights, right? So with some parameter gamma. So this constraint could be, say, the L2 norm, so the typical Euclidean norm. So this would be, say kind of the so-called ridge regression. So whenever we have, let's say that, I mean, in principle, you would need to have that the model is, strictly speaking, a linear model, so some kind of WT vector product with the input x. But you can extend this in other situations. But so every time you have that, you impose to these weights a penalty for large squared values, right? You have the so-called ridge regression. So basically, it means that you typically want to find the W that minimizes this loss function. So if it was only the error, it would be the error, okay? But then you say, yeah, but okay, I penalize. So every time that I have large W's, actually this fights against. So I will try not to choose solutions where the W's are large. Or you have the L1, this is the lasso. So this is would be the sum of the absolute values of the W. That would be the L1 norm. And this is a regularization that promotes sparsity. So I'm going very fast here. If you're interested, I can dig deeper, but this is typically what I do in a more basic machine learning course, in which so there is a geometrical reason why the L1 norm will prefer solution in which some of the W are 0 and some other are not 0. So in this sense, solution will be sparse. So this would be, in general, what we have as regularization in for any type of model class Y here of W. We would have ways to regularize our result. So there are algorithms that implement some kind of regularization in this specific sense to neural network optimization. So the L1 not so much. There's some problem, but the at least as simply stated as this, but the L2 norm, it is pretty common, so that you introduce some kind of regularization on the actual weights of the neural network. But there is more than that. So one can show that the depth of a neural network is by itself a regularization. So this is not easy to show, but you can imagine that you are taking these linear combinations, and then you apply this, say, smooth activation function. That's important that you have a smooth one. And so you can see that if you look at the representation of an input function, after each layer, it is smoother and smoother. Right, so you give a very rough input function that reacts a lot to any kind of noise. If you open up every layer and look how it has been transformed, because at the end of the day, it will be every layer will transform the input function. It will be that function smoother and smoother. So number of layers in your neural network act as a regularization. To be more specific, with the same number of nodes, if you have just a one hidden layer flat neural network, if you rearrange the same number of nodes in layers, you will have a regularized solution. So you don't have to do anything. You have a kind of built-in regularization because of the architecture. And this is one reason why in general, people do not bother very much about regularization in neural networks. Then we have another strategy for regularization that is called dropout. And this is related to bagging / ensembling. So what I have shown, and I think in the first lecture, that if we have high variance model, we can cure this high variance by taking the average over several such models, training with slightly different training data. Or instead of changing the training data, we could change a little bit the parameters of your model. Like if it was a random forest, you could have each tree in the forest that it is trained with different input features. So you have a set of input features, and then you take out some of the input features, so you train every single tree in the forest with different inputs. So it is forced to be a bit high bias, because it will not describe the whole thing, but if putting all together, it will have it will reduce the bias as well, but also the variance will be small, because you take the average. So that comes from the just statistics. So there is a nice way to do this kind of bagging ensembling idea with neural networks without training several neural networks at once. And this is done by randomly switching off nodes. So that means you go over all the nodes and you take a random number, and then you have set your probability. So if this random number is smaller than the probability that you set, typically small, so say 1%, you have the probability to switch off the node. Switch off means that you set all the weights coming to that node to 0, so that we'll also have 0 output. And say for one specific training data or a mini batch, that node is dead. So randomly, 1 over 100 or whatever, so 1% of the nodes will be switched off. And then in the next mini batch, you change which nodes are switched off and on. So one can show that if you do this over and over through epochs, you are approximating the training of 2 to the power n, but this is number of nodes, networks. So basically you are looking at the average result of all possible sub-networks that you obtain by having each subset of nodes switched off. And that's the power set of that is 2 to the power n. The convergence of to the actual final is not super fast, but the convergence of the standard deviation is quite fast. So so basically, if you do that routinely over the training, you always achieve a lower variance estimator because of that of this trick. And sometimes in literature you see that the justification is also you avoid to have over specialized nodes, so that you could track back that some nodes are specifically looking at a certain part of a function in the input space, and this is typically not very robust. So if you do that, you distribute the information over all the nodes. That turns out to be better, but this is starts to be a bit mysterious. What you can see much better statistically is that you are approximating the training of these all possible networks with all some nodes that are switched off. Okay, so and this is called dropout, And incidentally, so this is what I've described is the dropout for training. You can do the dropout in inference. So when you use a network that has been trained typically with this technology, you can also randomly switch off nodes when you make predictions and do it a few times. That means you can do it only one time, you just make the prediction. So you have clever tricks so that you simulate this kind of switching off nodes, and then you effectively have that the network predicts a distribution of values, because each configuration of switched off nodes will have a different output. And one can show that this is the same at some point converged to training so-called Bayesian neural network, in which instead of learning nodes, weights, you learn distribution of node weights over all the possible input. The actual Bayesian neural network, the one that instead of having weights has a distribution for each weight, it's notoriously a nightmare to train, but this simulation of Bayesian neural network with dropout in inference, well, from the architecture point of view, it's costless, and from the evaluation point of view, it's a little bit more expensive than doing one evaluation. You don't really do it n times. There are tricks to save the information and combine it differently so that you get a distribution of results. So actually what you get is average and standard deviation. So you say everything is Gaussian at some point. And so you get some kind of error estimate or uncertainty quantification. So not sure we'll come back to this point, but this is a way to do this. I've used in some publication of mine, and so the appealing part is that from a computational point of view, it is essentially inexpensive compared to doing the single evaluation. Other methods to do uncertainty quantification are much more expensive. So, but one can show that this Bayesian, so this dropout inference sometimes has a bias. So it's not the universal solution, otherwise it would be universally used. Anyway, but in training there is no problem. You are just making the training more robust by doing this dropout. Last point about regularization. So it is some kind of regularization, is so-called early stopping, also that you find often in literature, and it is exemplified by plot. So if we look at the error as function of number of epochs, so we would have a training error. The training error will typically start large and go down. So that, of course, so keep in mind we are starting from random weights, right? So different from traditional methods in which you have, given the training data, you have a closed form to evaluate the weights, in which case your training error is very small, sometimes even zero if you have too few data points. You have more data points than weights. And so the training error will increase with the number of data points. In neural networks, typically, you will see. So this will be the training error. Will decrease as the number of epochs. It's not the number of data points here. It's just how many times you use the same data points to do the training, right? So, but just to be clear, the validation error will start large by construction and will also decrease. But then one typically sees that at some point it starts going up, because now the network is over-specializing over the training data. It's overfitting over training data. So typically one monitors the validation error, and when it starts increasing, you stop your your training here. So that's called early stopping. Caveat, there are many instances in which this validation error has wiggles, and there is a full literature saying that actually don't stop at the first minimum, wait for the second one, because it will be always be lower. Yeah, okay, depends on your data typically, and many other variables, but again, it's worth noticing that yeah, if you apply neural network, maybe you want to wait a little bit more and see what happens just before stopping, say here, because you see that it's going a little bit up. Okay, but again, so this is the so-called early stopping. Nothing of this you see is, I mean, I'm just writing words and explaining a little bit without equations, because so you find, of course, in literature also the mathematical grounds for all of this, but of course for synthetic data, so you build up, you construct you can prove theorems, but by constructing specifically distributed training data, that is never what you have in real life. So as a kind of summary here, all these are technologies. So certainly we use Adam optimizer, we use mini batch, and well, we use depth for sure, and typically also dropout and early stopping for our training. Okay, so I think I'll start introducing now the convolutional networks. So these are the kind of architecture that one construct to do the so-called pattern recognition, and by pattern recognition we mean the following. I have some aids. So what you see here is so this is a spectrogram, which you have time here and frequency here. So let's say that one is recording some well, any kind of ambient noise, but let's say that there is some speech, and so what you would see that you have some frequency patterns appearing over time, and then you want to recognize in such spectrogram if somebody has uttered some word, welcome. So welcome would have a specific pattern in this spectrogram. So let's say that it would be something here. I have no idea, but so that specific instance in the time series will be recognized as our positive outcome of the recognition, right? So it is a. So what we need is a pattern recognition, because we know how the signal that we would like to find looks like, but we don't know when it happens in this time series, and so this is kind of the one-dimensional case. So we are looking for some specific pattern in frequency. So, of course, frequency is now here. This would be some intensity, and we don't know when it happens in our series of data, and probably even easier to understand, but essentially the same problem is that we have some surface, and you're looking for some kind of specific structure on a surface, and you know that it looks like a star like this, but you don't know where it happens, where it is found, right? So you want to have a way to recognize if such a pattern appears in your image. So it could be just a photo or a microscopy image or same. So yeah, let me go back to this one. So let me build up how one goes from this say challenge to a convolutional neural network. So the first step would say, okay, do I have also my neural network? 1 second, so that I don't. Okay, so the idea is that I have a neural network that will get, maybe I do like this. So as I was trying to say, we have actually some kind of signal at a certain time. And this neural network is trained to say the probability that we have seen this signal in that particular time, right? And then we kind of apply the same network. This is very important that it is exactly the same network. So this network is trained to say essentially 1 if it finds the signal and 0 if it doesn't, or some intermediate value if it is somewhat, you know, you are in the next time step and there is some echo of that or some jittering in the representation, and you see a trace of that signal, so a bit dampened, so you have some intermediate value between 0 and 1. And then yeah, so essentially what you would have then, you could think as yeah, somewhat applying this network over and over at different time steps, and then have some kind of summary of what everybody has found, and you have some kind of say OR, right? So there is another layer, another neuron that will collect the information from all the networks and say, okay, if at least one has seen something, I give positive outcome, otherwise nobody has found. Plus you can record where it was found, of course, but that's a kind of side effect. And this OR is actually will be a softmax, so that what this is very used in the field. So it's always like exponential of the output over the sum of the exponential of the output. So this would be yeah. So you take all the y's here, so whatever softmax of I will be taking the exponential of that input normalized by the sum of the exponential, and this will give us a 1 if something happens, or 0 not, and then there is some intermediate value if we have seen a portion of something. Yeah, so this would be the basic idea. So the I had some keywords here. So this would be called a scanning network with or yeah, sorry. You could think also as a instead of a small network like this, that it is kind of scanning the signal. You can also think as a overall network where the first layer would be the union of all these first layers and so on and so forth. So you would have a large neural network with the, I don't have to change anything in the picture, it would be exactly like this. But compared to a fully connected neural network in which you would have all nodes from each layer talking to all the node to the next layer, you would have only subsets of nodes that talk to each other. And even more importantly, so this, maybe do with another color, this specific node here would be exactly this, so weight would be exactly the same over all the instances, right? So imagine that you are going to train this network, you will impose that that weight is always the same. Independent. So there will be maybe only one of these subnet that will see the signal, but if you update the weights because of that event, you update all the weights in all the subnets. So this would be called shared parameter network. So big word to say that we can think at this scanning network as an overall network, but we impose constraint on the weights. And to go back to the nomenclature, this can be also, it should be thought as a regularization, because if we have that if we look at the weight metrics of a fully connected neural network, it will be dense. So essentially all the weights will be different from zero. If you just construct a network like this with shared parameter, you force it to be block diagonal, right? Because only some of the weights will be different from zero. You can rearrange so that you have the first block top left. The most important thing is that this will be exactly the same repeated because you force that the weights are the same. So all this will be zero, there is no connection. So this is a regularization because you impose that most of the weights are zero because of this. So let's say this is also a way, you can always say take your input and try to train a multi-layer perceptron completely agnostically and say, okay, I make as many layers as I need and then try to train. There would be a solution, probably. Everything else in the literature is designing architectures. Designing architectures means imposing some kind of regularization because you design that some weights are zero or because they do not exist at all. Some connection do not exist at all. This is, of course, true also for a modern language model, so a modern transform-based language model that, of course, is a bit ironic that you have, I don't know, tera parameters and it's still regularized. I mean, it could be much worse if you do it a multi-layer perceptron for the same task. Okay, convolution. Convolution, next point would be, I need the aid of my things here, 1 second. So I need this one, probably like this. No, I wanted to. Okay. Pasted. Okay, first of all, let's see a sort of sketchy version of this scanning network. So let's say that we have essentially what I have already explained. If I write it in pseudocode, so for time, so that will be the one-dimensional version in which I look for a certain signal or some pattern in time. I define a certain window, so I will, I have to define which time window I look at. This is defined by this k. So I look at the segment of my input that has a size k, so it goes between t and t plus k minus 1, okay? And then I look at the output of the multi-layer perceptron applied to that segment, right? So this would be this subnet. It's a fully connected subset of the whole network. It is a multi-layer perceptron, and then apply the softmax in order to see if that signal is there or not. And more in detail, okay. I could write in this way, so I am no, not this one, the other one first. Yeah, sorry. Okay, so I can expand that the multi-layer perceptron better from the previous pseudocode. So again, we go over time, and then what we are doing is going over layers, nodes inside layers. Okay, the first layer we use the input. Otherwise, we are propagating our signal, our input in between layers. So we calculate the affine transformation here, and then we use the activation in order to get the y at each layer, go over all the layer. At the last layer, we evaluate the softmax. So it is exactly what is written here. I've just expanded what MLP of X segment means. And now here is one of the key tricks in order to get to convolutional neural network that is somewhat how to say, guessable from this representation, in which we have laid down all the networks so that you combine the first layers of the subnets in one big first layer, and then the same for the next layers. So, but from the pseudocode, we can also notice that these two loops can be exchanged because nothing happens in between the first and the second, right? So from a computational point of view, very little changes. But from the conceptual point of view, it is very nice because we say, okay, we have that each layer goes over the signal so the whole signal. So because now we loop over the time, so we are giving to the first layer the signal at different times, and then we propagate it through the next layers, and afterwards, after the whole signal has been ingested by the first layer. And this is one, let's say, conceptual step before we go to the full convolution. So we have this shared parameter network properly rearranged conceptually and algorithmically. Yeah, okay, I think I need to stop probably for today. So the next step will be where I will start next time is distribute. Oops. So we have the concept of distribution. That is the second conceptual step to build a fully convolutional neural network. And just to wrap up here, so the overall idea here is to construct some efficient neural network that whose task is to find if a certain pattern is present somewhere over the input signal. So it could be a picture, or a one-dimensional spectrogram, or any kind of time or space resolved signal, or both. Also for a 4D stem you could have something like that, a bit complicated, but the overall idea is that I'm looking for a positive, and I want to see if the network finds it. And spoiler alert, you can combine signals, meaning say I can look for certain pattern, another pattern all together, and have the networks telling me which of the patterns were seen, not just one pattern, so you can train an overall network. And all this reasoning is in order to make the network efficient from the point of view of the number of training parameters. Because if we could build a huge multi-layer perceptron, but that will scale very horribly, as I will show next time, a bit of back of the envelope calculation to show how much you spare when you build this convolution network. So this will be task for next week. Okay, thank you.